Good morning. My name is Renee Puusepp, and I'll come from Estonian Academy of Arts from the Department of Architecture, where we've done this study of pedestrian movement in the cities. So we particularly looked at one city, that's our capital, and one square kilometer in the capital. So this is actually being commissioned by the city planning office and three shopping centers in the city. So it's quite telling actually where the interest comes. So basically it's big private enterprises that want to draw more people to their businesses. But it's also the third part is the public side or the planning office that kind of says that you need to actually make the public space really public and usable for inhabitants. So it does actually relate to the topic of this this conference, Humanizing Digital Reality, quite well as well. And I'd like to briefly explain how. So we realized that yes, public space actually drives pedestrian movement. So the physical shape of the city does influence how we behave in the space, and we believe that the way we behave and the way we move in the city should also influence the physical shape of the city. Hence, it should be in some sort of feedback loop. Now the screen image that you see is actually very straightforward real-time feedback between agents navigating in the space, leaving traces behind, but picking up their own traces. So, and this type of real-time feedback is obviously not possible in the city, or at least because the planning cycles are much longer, and then you can't imagine do actually people shaping the city with their movement. However, we think that it is possible to build a similar kind of feedback, and this would actually need us observing how people move in the city. So we see how they go around, what are the physical characteristics, what are the spatial qualities that influence their movement, and based on these observations, we can create a simulation that in turn can be used to analyze the future scenarios of city planning. So hence the digital reality or the proposals of how to reshape the physical environment and hence also the physical environment itself. So to put our study into context, I think there have been lots of pedestrian movement studies. At the large scale, we have the studies dealing with cities. So usually these are actually used graph theoretical approach. So the city is reduced to a number of vertices and edges. We don't think it's really appropriate for pedestrian simulations because you simply cannot reduce the sort of the walkable landscape into straight paths, as you could do with traffic modeling. So on the other end of the scale, there's crowd simulations and physical pedestrian dynamic simulations, which are good for evacuation simulations, for example. But we are more interested in sort of mesoscale and to deal with the public space at the street level, within the street canyon, but also taking into account the width of the pavements, also where the sun is shining, or what all other spatial qualities. And yeah, so basically what we realized in quite early on in our studies that pedestrian movement in the cities is really complex. It's not something you can easily grab and create logical rules and put it in the box and deliver it somewhere else. but there are multitude of user types. There are different pedestrians behave in a different way depending on their age, sex, their physical capacities, but also the spatial qualities are really important. So these are temporal or climatic factors actually that influence whether the sun, if the sun is shining outside, people don't tend to go indoors, or if it's snowing outside, as it often happens in Tallinn, people do go inside and spend their time in supermarkets. So how do we want to tackle this? We thought that it's essential to experience this kind of movement from the first person perspective. Thus we actually followed people on the street. So with our handheld GPS devices, we thought it's not enough to just count people on the streets, and none of the technologies actually that's available at the moment are affordable to us, or actually do what we want. So we are really interested in understanding what are the spatial qualities that make people do verge off the shortest paths. So people don't use always the straightest roads, they wander off, and we believe that there are some spatial qualities behind that, what makes them behave this way. So shortly, this is Tallinn, if anyone knows. If not, then it's actually an area between the harbor and the modern city center. The old town is on the left side. It's been behind the Iron Curtain in the last century, and the last 25 years it's been actually developing quite fast, and only now actually getting to the really critical point where we need these kind of studies. Or actually, we should have had it earlier, but we didn't. So a little bit more about the methodology. We actually kind of fenced the area of our study. So we said that these are the street sections, these are the gates that people enter or exit. Other gates are also the bus stops, and some of the, you can consider apartments and offices as sort of gates as well. So basically we just using our smartphones, tap the GPS, and then we follow the movement. When the person actually gets out of the area, we stop the clock. Obviously we don't take any personal data, and we don't really follow people, we just follow the movement. Anyway, these are some of the results, and if you think back of space syntax studies that kind of operate at the similar scale, for example, Michael Batty has done a study in Britain and looking for movements. They're using sort of random walkers to simulate the movement. That's not what we observed actually in the city. People don't move about randomly. Only the one on the top right corner is kind of a random movement, and it's probably a tourist, but it's only, I don't know, 5–10% of people who are doing. Most of people actually know where they're going, and take quite conscious decisions on the road, I think. Now, we collected about 500 of these paths in one go. Earlier, we've done earlier studies as well, and when we aggregate them, it kind of starts telling us where are the possible sort of densities of pedestrians in the city, and what roads people are using, what they are avoiding. Now, in order to understand whether people are using really the shortest paths or aren't using, as we hypothesized, we had to reduce it into a graph. And this is basically showing all of its abstracted form, showing all the potential routes that pedestrians that we observed have taken. And funnily enough, it kind of became an analytical tool in its own right to understand the qualities in the city. So you see some of the streets are more pedestrian friendly, they are more often crossed than others. And indeed, that's what we observed in the in situ as well. So, and then we can analyze each individual path, whether it's the shortest one or not. So the red one is the shortest one, and the black one is the observed one, and we can compare it to one another. I mean, there is a little caveat that actually people don't use this tram line, so to speak. Some people are actually crossing the 6 lanes of traffic with illegally. So this kind of the network is kind of made up based on the observation, and thus the comparison to the shortest path is perhaps not scientifically accurate because we haven't observed all of the possible movement paths. But what we found out, bearing in mind the caveat, is that only 35% of people using the shortest ones. So yeah, we can't take that as an exact number, but it's quite telling. Now, if we wanted to take this to simulation, we can't use the graph anymore because you can't simply reduce public space into graphs. So imagine a public plaza, for example. So how many nodes and edges do you have to use to actually show what are all the possible ways to move across it? So instead, we imagined the cityscape as a sort of landscape of walkability values. So with the remark to James Gibson and the affordances of objects, we thought that the city is kind of elements of that allow you to walk on. So it's kind of affordable, whether element of a city is affordable for walking. So some elements are not really, I mean, buildings not really walkable. So, but others are. I mean, pedestrian sidewalks are quite have a really good walkability value, while roads still walkable, but they have really bad walkability value. So it is kind of a landscape of opportunities, and obviously it depends on person by person, but we can kind of approximate the sort of some kind of a generic value based on our observations. Now, this landscape of walkability values can be actually turned into a computational landscape. So we can say we can compute the proximity maps. So, for example, how far is a supermarket from a bus stop? And this is calculated based on the walkability values. So, hence, it's not a metrical value, but it is a perceived distance, or a cognitive distance, you might say. Now, this is a little bit closer up. You can see how the proximity values are actually propagated from the center of this building, and you see the public park on the left-hand side have actually a much better, well, I should say, a shorter perceived distances than actually areas that are metrically closer, but on the other side of a busy road. Now, based on top of these proximity values, we can use very simple agents with the 3 sensors. They just sensing the proximity values and roaming from the origin point to the destination, kind of leaving the trace behind, and then we can start seeing actually where the simulated walkers go. Done some sensitivity analysis, so with the basic road and the pedestrian crossing, seeing actually what are the sort of close enough values to make people use the crossing, or actually if they far enough from the crossing, would they actually cross the road itself. Some screenshots from the simulation. It's actually a pretty nasty place in Tallinn. If anyone's been there, it's in the city center, and there's a pedestrian tunnel. Obviously, no one would do it anymore, but it was built in the 90s, and we observed quite interesting behavior there. Some people actually ran through the tunnel, mostly young males, and other walkers actually took a detour. So that's what we observed, and that's what we were able to actually simulate as well by just adding different walkability values to the tunnel itself. Early simulations of the current situation. So essentially we have a number origin and destination points that have been given by a third party to us, saying that where people potentially come and where they go. Some interesting points actually that the simulation started telling us is the simulated workers crossed a street in one particular place, and of course, I mean, that's when we thought actually we could have observed it, we didn't. But if we think back, yes, that's the place I've crossed the road several times as well illegally. So it's kind of the simulation starts giving us some actually pointing out the possible problematic places. Now we can take these simulated paths and do further sort of statistical or quantitative analysis on top of that, and say where people possibly end up if the conditions are as we used in the simulation. Now, but perhaps more importantly, once we get it close enough, the simulation, to what we observed in the city, we can actually start feeding the sort of future city planning scenarios into the simulation model. So this one actually shows there's a new high street and the new central new park, Tammsaare Park designs that have been proposed, and we can start analyzing these designs with our tools. Obviously, it's not. We don't claim it gives you the absolute truth, but it gives you another perspective of how the design might behave. And this is a little close-up. It's still completed work. We're looking for the sort of estimated origin and destination matrix, so where people come from and where they go. There's another functional analysis behind it. It's not done by us, but our partner. So, and to conclude, we believe that sort of a simulation or the walking in the city is very much dependent not only on the physical shape of the city, but also on the social and cultural context. So we don't think that you can actually create a simulation that is applicable to every city in the world, but you do need to base the simulation on the observation, so hence the simulation models need some localization. Thank you.
Any questions for Renee? Areto, do you want to?
Do you take into account time-based things like traffic lights, or like, you know, you cross a road when there's a break in the traffic rather than?
Yeah, we do actually, in a way. We say that wherever there's a traffic light and there's a pedestrian crossing, it actually has a smaller walkability value than those crossings that actually don't have the traffic lights, because you kind of have to wait a little bit. And from the qualitative studies, that's actually been kind of confirmed as well.
But I guess in the kind of the shortest route, your shortest route when the light goes green and you go across it, and then another time you just go a different way around because it's just gone red. So how can you kind of accommodate that sort of?
We don't think actually we need so accurate models in time-based, but you're right. I mean, it can be enhanced and actually say so some of the like Bedflow or other tools can do it, but it's more intended for a smaller scale studies. So for larger or kind of mesoscale study like that, we don't think it's actually makes so much different. Plus, we don't actually say that here's 100 people, how they move, and here's 90 people go this way and 10 people go this. We're more interested in actually trends.
Sorry, my question is, does that include redevelopment? Are you going to get a time scale that actually shows how changing the city changes the path?
No, I mean, it's, well, first we want to kind of understand how it behaves at the moment. And whether we can actually project it into the future, I think it kind of just it's another simulation based on the same observations that we used and the kind of simulation settings.
Thank you very
One quick question.
Oh, sorry, one more.
Just a quick question. Could you explain how you were getting GPS data from 500 people? What kind of also arrangement you needed to make and so on?
Well, it's quite laborious, so we kind of use students to help us to track them. So there are a couple of ways, but I mean technical ways how you could use the movement traction cameras. But for a scale of the city that we used, it's kind of really tricky. You could also think of using some sort of mobile positioning, which is not accurate enough at the moment. You could use some sort of Wi-Fi or Bluetooth beacons or anything like that. But that involves people knowing about the study. And this actually is another topic, but it kind of, if people know that they've been actually watched, they might behave differently.